Okay, we study C5, permutation and binomial theorem. So I believe you are very familiar with the permutation of binomial theorem. You learned in high school. I believe so. Perhaps not, because there are many tracks. So some students are very weak in both math and physics. Anyway, we study permutation today. List all permutations of two distinguishable elements A and B. Okay, A and B are different. And permutation is coming from a set, and either we repeat the same selection or not. In here, we distinguish A and B. So in that case, A and B can be listed only once, and we have n tuple. N tuple means that we have n distinct numbers, and we list them order by order, A, B, C, D, E, F, G, and so on. In here, n equals 2. So everybody knows that there are only two cases, AB or BA. We define a simple operator that is called the permutation operator, denoted by pi and I left to right arrow j. That means we exchange ith element in the order of the list, ith element and jth element, we exchange them. So A, E, C, D, B, something like that, after applying this operation. Because we have a first and second element only, the only possible way of permutation is exchanging 1 and 2. Sure, you can try exchange something with itself. That is an identity operation. It does not affect that there is no difference at all after applying this. So this is nothing but an identity operation. So if we exchange the first and second elements, then A, B is transformed into BA. And that is different from A comma B because we assume that A is not equal to B. Just like this, repeated multiple permutation is allowed. What about exchanging first and second twice? In that case, this squared permutation operation doesn't change anything. It returns to the original form. So this any permutation exchanging any two elements twice repeatedly, then you will get the same result. So that is a trivial identity operation. As a result, we find there are only two permutations. We define the signature of the permutation. Signature, my signature is this. This signature does not mean this. This is a sign, either positive or negative. We define a Leibniz-Civita tensor that defines the signature of permutation. In case we have only two numbers that are listed in order, we have these three cases. Even permutation is, for example, 1 and 2. We define ordered one whose indices are increasing monotonically. We define this as the first one, If we have 3, 1, 2, 3, and 4, 1, 2, 3, 4, simplest ordered list, we define it by even permutation. From this, I'd like to exchange any two elements from this. You can find, if we exchange the first two, you will get 2, 1. They are different because I have defined all of these to be even permutation. This one, I have obtained this new permutation by applying pi operator only once. Once is 1, 3, 5. These are odd numbers. Odd numbers. Repeat permutation, applying permutation by an odd number of times, you will get an odd permutation. For example, I exchange 1 and 2 twice, then I would apply the permutation operator twice, so what I get is even permutation. If I apply this permutation operator for first and second once, then I would get an odd permutation. Therefore, in here, when n equals 2, we have, in case a equals 1 and b equals 2, the only even permutation exists. If I apply a permutation operator once, what I get is a 2, 1. That is odd permutation. And why don't you release our condition that these two numbers are different? So we allow the same values. For example, 1, 1 and 2, 2. So in that case, these two cases cannot be obtained by any permutation of 1, 2, because permutation of this 1, 2 can only generate either 2, 1 or 1, 2. So we say 1, 1 and 2, 2, they are not a permutation. The signal function for this permutation is called the Leibniz-Civita tensor, and therefore epsilon 1, 2, this is for an even permutation, that is a positive 1. Epsilon 2, 1, because I have applied the single permutation to 1, 2, I would say it's a signal function, the Leibniz-Civita tensor for epsilon 2, 1 equals minus 1. If it is not a permutation, for example, epsilon 1, 1 or epsilon 2, 2, these two cases is removed by setting their values to be 0. This is very, very important. For example, from elementary school, you learned how to measure the area of a geometric object. For example, if you have a rectangle, area of rectangle is non-vanishing only if two adjacent sides are making an angle theta. If this angle becomes 0, it collapses into a single line, straight line. It does not create any area. When we apply this idea to the three-dimensional case, we can find a non-vanishing volume only if these three sides are linearly independent, that they are not on a single plane. As soon as you make it collapsed into a plane, then this one does not make any volume, something like that. Lebesgue tensor shows whether your geometric object has its own volume in 3 dimension, own area in 2 dimension, and so on. What about the permutation of 3 numbers? I'd like to identify A, B, C to be 1, 2, 3, and usually they are to be identified with the x coordinate, y coordinate, and z coordinate. Then the permutation of these 3 ordered number will give you some idea whether this object may give you a non-vanishing volume or not. Permutation operator can be defined among the 3 elements. So exchanging 2 elements out of 3, we have only 3 cases. As you know, exchanging 1 and 2 is identical to 2 to 1. So they are identical to each other. So there are only 3 distinct possibilities of permutation operators. We begin with 1, 2, 3 or ABC. They are all different. And we'd like to apply these 3 distinct permutation operators. Then 1, 2 is to be exchanged as 2, 1 and 1, 3. So this becomes flipped. Wait a second. 1, 3. 1, 3. This should be 3, 8. There's a typo. So this one should be C, B, A. Okay? And it's a 2, 3. Exchange these 2. So your result is A, C, B, something like that. Again, identity operation is no change. A series of permutation, first, second. So we have exchanged these 2 elements, and then 2, 3. Then AC. So keep this B the same and AC, CA. So in this manner, we can apply these 3 permutations repeatedly. But everybody knows that the listing distinct possible ways of 3 numbers, you have 3 numbers, and you know you can put 3 of them, and you have lost 1 element out of 3, then there are 2 ways to fill this, and then you are left with only a single one. So you compute this one as a 3 factorial. That is number permutation, something like that. But the viewpoint of permutation in this manner looks cumbersome. However, it is a very, very efficient when we have a number of particles and number of indices. This is the simplest way, this rather than this. Anyway, even permutation, we begin with the simplest permutation 1, 2, 3. From this, if I exchange any 2 elements, for example, A, B, then I have only a single permutation, that is odd permutation. What's that? Exchange these 2, and we have this. Why don't we replace this guy, these 2 guys, these 2, and the result is a single permutation. Odd permutation, the answer is A, C, B. And then we exchange these 2, keeping B the same. So that is this. So all these 3 permutations are obtained from the original even permutation by applying the permutation operator only once. That is an odd number, so we claim that they are odd permutation. Remaining piece can be obtained by exchanging, for example, in here, keep this one and exchange these two. You will get this. However, to arrive here, you have applied a single permutation and another single permutation. You have applied two permutations. Therefore, you end up with an even permutations. Okay. In a similar manner, what's that? AA the same. Why don't you exchange these two elements? Then you arrive at here. Again, this one is an even permutation. In this manner, any permutation n elements you have n factorial. However, among them, they are sharply divided into two pieces, even permutation and odd permutation. That is 1/2 of n factorial, 1/2 of n factorial. These are even permutations, and these are odd permutations. Because we are considering n equals 3, we have 3 factorial equals 6 permutations. Among them, we have 3 even permutation and 3 odd permutations. These 3 permutations are called even permutation. These 3 are odd permutation. Except that we can apply arbitrary number among 1, 2, 3. So we have all possible cases, 3 by 3 by 3, 27 cases. So except for these 3, 3, so 6, so we have 21, nothing, 21, no permutation. Okay, so let me see the tensor for 3 elements, 1, 2, 3. We define +1, -1 for odd permutation and no permutation. Everything is 0. Anyway, only if these numbers are distinct, it will be related to non-vanishing volume in 3-dimensional space. I have replaced A, B, C with 1, 2, 3 respectively. Evaluation, we have epsilons. Because we have epsilons, everything is either +1 or -1 or 0. I told you even permutation, number of even permutations and number of odd permutations, they are the same. So we have 1/2 n factorial +1 and 1/2 n factorial -1. We add them up. Same thing with different sign, it cancels exactly. Therefore, Lebesgue tensor summed over every indices. Every indices. This is the most general case. It is not restricted for either 2 or 3. N cases. There are n indices to be permutated. They are all summed to get 0. What about this? You know, this is either +1 or -1. I have squared. +-1 squared is always a positive 1. Therefore, if I sum these, all of these, what I get is n factorial. A very simple case. Looks very, very complicated, but it is nothing but n factorial. Okay? There's a typo. And when we compute n factorial, we need to define this one. To simplify, a 0 factorial is I do not multiply anything, so it is not, it does not represent you multiply 0. No, 0 factorial means I have not multiplied anything. Therefore, and I will multiply something. So it is good to define 0 factorial to be 1. Simplify the binomial coefficient. Binomial coefficient that is obtained by expanding this polynomial. You know it is a to the n, n, a, n minus 1b, and so on. These coefficients are called binomial coefficient. It's the coefficient of a binomial. There are two terms to be added. So binom, so two terms. So nth power. After you expand this, any term to be added has a coefficient that is called the binomial coefficient. And I believe everybody knows that. Not everybody knows this symbol, but as far as binomial coefficient is concerned, at least you know the Pascal's triangle, for example. So I believe everybody knows the binomial coefficient. And there is a special notation, something like sigma. Sigma is a sum, and sigma and pi, they are the same, repeated one, except that sigma add a1 plus an. Pi multiplies ak. This one is a1, an, multiplication. Okay? So by definition, binomial coefficient is this. And n factorial divided by k factorial, n minus k factorial. N factorial is number of powers. K is in the middle. I have k, and if I choose a by k times, then I need to choose b by n minus k times. Therefore, the multiplicity must be multiplied. That is the binomial coefficient. And I have total n elements to be listed in order. That is n factorial. And I have identical a's by k times. So I have overestimated number. This is overestimated. I have to cancel. I have to revoke what I have computed too much. So this k factorial should be removed in the multiplication. In addition, b repeats by n minus k times. So the same thing, they are not permutation. So that should not be considered a distinct permutation. I must divide it by n minus k factorial and multiply everything all together. So this is k factorial, this is n minus k factorial, this is n factorial. And why don't we remove this from the numerator and keep this one the same, that is a k factorial. And it began with n, and it began with the n minus k. So after the cancellation, we left with n minus k plus 1. This one cannot cancel this. Therefore, this is the binomial coefficient. By the way, we have a Pascal's triangle formula. I hope you can follow this calculation. This is the proof of Pascal's triangle formula by applying mathematical induction. So If you are able to prove this, that is Pascal's triangle. You learn this, right? 1, 1, 1, 2, 1, 1, 3, 3, 1, 3, 3, 1. What's that? This one is a squared plus 2ab plus b squared and cube. Something like that. So these relationship among the coefficients, binomial coefficients, is called the Pascal's triangle. So if you can prove this Pascal's triangle using these calculation, then you can expand a plus b to the nth power for any non-negative integer. Actually, Newton found that Newton generalized this one into partial fraction. There's a fractional power. So that's the beginning of the Taylor series expansion. Okay. What are the dimensions of the physical quantity? So you should be familiar with how to count the dimensions. Please read this through. By the way, this part is very, very important for the application to find the Bernoulli's definition of Euler number. Some of you must know this comes from this identity. This expansion of a plus b's nth power in here, I copied this, and then I would like to divide this one to be nth, the kth power of n. And let's write it. This one, we just have shown that this binomial coefficient is this divided by k factorial. Therefore, we have this divided by k factorial. In addition, I'd like to divide this one by n to the k. N to the k is divided. This is n multiplication of n by k times. And what about this? It began with n plus 0 to it ended with n minus k minus 1. Therefore, from 0 to k minus 1, I have k factors. K factors. Why don't we divide each factor by n? So I can distribute everything in a single factor. Then this one becomes 1 minus 1 over n, 1 minus 2 over n, and so on. It ends up with k minus 1 divided with n. We keep k a finite number, very important. In that case, these term in every factor vanishes as n goes to infinity. Infinity, then, is exactly 1 over k factorial. As a result, the reason why I have attached this is I'd like to compute this. A plus b n. Substitute a equals 1, b equals 1 over n. Then what I get is sum of this, summed over k from 0 to k equals 0 to n, 1 over n, k, n minus k, and k. This is exactly the same as this one. 1 plus 1 over n to If we take the limit n goes to infinity for any finite k, this is 1 over k factorial. So this one is greatly simplified into a simple form. So it is nothing but 1 over 2 factorial, 1 over 3 factorial, and so on. If you add everything up, you will find E. We will compute this one later. That's it for today.